My name is Kalina Borkiewicz. I'm a senior research programmer in the Advanced Visualization Lab, which is at the National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign. I'm going to talk to you about storytelling with data. So, to get started, let me start with telling you a story. A few years ago, in the middle of a cold winter, a friend of mine was driving around a four-wheeler, misjudged the level of water and ice in a frozen river, and ended up getting the vehicle stuck in frozen water. A group of friends, including myself, came over to try to help him figure out how to pull it out from the water. One friend put trash bags on his legs to try to stay dry, and he waded into the river to attach a chain to the vehicle. We tried towing it out with a pickup truck, but almost immediately we popped a tire on a broken tree trunk. So, the truck quickly became useless. Thankfully, the friend had access to a tractor, so we got that to try to pull the vehicle out. None of us actually knew how to drive it, but we gave it our best shot. As soon as we started pulling, though, the tractor started slipping on the frozen dirt and began to fall into the river, too. So it seemed like this day could not get any worse. But before the tractor fell into the water, just in the nick of time, we found that there was a four-wheel drive setting that had been turned off, so we switched it on and we were able to pull out the four-wheeler. We towed it all the way back to my friend's house where we celebrated our victory. Now let me tell you that story again in a different way. A friend of mine had a four-wheeler. It got stuck in frozen water and we tried to get it out. First, we attached a chain to the vehicle. Next, we tried pulling it out with a pickup truck, but that didn't work. Then, we tried pulling it out with a tractor. It didn't work at first, but eventually it did. We celebrated. These two stories had pretty much the same information, but they were not equally effective. It's not the facts themselves that matter. It's how you tell them to another person that determines how much that person cares about what it is that you have to say. At its core, visualization is a type of science communication. Just like a podcast, or a dinosaur exhibit at a museum, or a lecture by Bill Nye the Science Guy or Neil deGrasse Tyson. Like with all science communication, there is a risk of losing your audience due to assumptions about prior knowledge and using science jargon that they might not be familiar with. Here's a comic by XKCD that makes fun of the jargon of rocket science by simplifying a diagram of a rocket to descriptions using only the 1,000 most common words in the English language. I say 1,000 instead of 1,000 because it turns out the word 1,000 isn't one of the most commonly used words in the English language. It can be tempting to think that people who don't understand our jargon don't understand it because they're stupid. That's not true. People's expertise lies in different places. No one is an expert at everything. As science communicators, it's important to find a way to make a science message accessible to different kinds of audiences without dumbing it down. In addition to this comic, XKCD has a web-based tool that goes along with it that you can use to try to rewrite your own text with simplified language. Here's an example of some jargon that I might use to describe the work that I do. The Advanced Visualization Lab creates cinematic visualizations of supercomputer data for immersive displays. Now, you guys are a scientific audience, and it's probably even difficult to really comprehend what this is saying, even to you guys. As you can see, in red, I'm highlighting the words that are not among the top 1,000 words within the English vocabulary. So here's a rewrite. The very good picture-making team creates movies of huge computer information for screens you can be inside of. While this is kind of funny, it's undeniably a lot easier for people to understand. I wouldn't actually want to use this exact text when describing my work, but this is a good exercise in thinking about word choices. There's no shame in using understandable language to help connect with an audience. The first step in creating a strong message is knowing who it is that you're trying to reach. My friend tells the four-wheeler story much more casually to friends than he does to his car insurance agent. If he was trying to tell the story to someone from the island of Hawaii in the 1700s, a lot of the things in the story would need explanation. Like what snow is, what a vehicle is, why water is bad for an engine. There would even be a language barrier. If you're presenting your science to 2 or more different audiences, you should consider either changing the presentation for every unique audience or making one presentation that's intended to be accessible to all audiences. Experts often have an easier time showing off the depth of their knowledge by using technical terms and complex images, but chances are your audience is more likely to be impressed with what you do if they're able to understand the work that's being done. What's more, it demonstrates more depth of knowledge when an expert is able to explain their ideas to general audiences. The most renowned scientists in the world are famous because they're good at this. The lab that I'm part of at the University of Illinois creates 3D scientific visualizations in the form of movies aimed at broad audiences that might include children, their grandparents, experts in many different fields, not just astronomy, and policymakers. We don't just visualize astronomy data either. You'll see in this little reel, here now we're looking at a tornado and all sorts of other types of data as well. A risk of speaking to a general audience is that you're going to bore the experts and confuse the novices. We avoid this by including nuanced details in our imagery that satisfy the most discerning experts in the field, but we focus on stories that are timeless and meaningful to everyone. Stories about topics like the origins of life, the workings of human society, and threats to safety. I'll skip ahead. But before I go any further, I want to take a moment to do a bit of vocabulary housekeeping because some of you may have watched that previous video and be thinking that this sort of visualization isn't the kind of visualization that you want to be doing for your work. So I want to clarify that visualization is a broad field, and I'm going to be using the word interchangeably to refer to a couple different types of things. The first is information visualization, which involves creating things like scatter plots, histograms, and networks in 2 dimensions that show relationships between data points. Then there's scientific visualization, which involves visualizing the 3D spatial nature of a data set. The positions of stars, the orbits of planets, the cosmic web, galaxies, things that have X, Y, and Z positions, or sometimes just X and Y positions, and those positions are part of what gets visualized. My expertise lies in scientific visualization, but many of the core concepts, especially the ones that involve storytelling, remain the same across the 2 visualization subfields and many other fields as well. So let's have a frank conversation about facts. Our minds are not wired to digest lists of facts. Consider this the next time someone's telling you a story of something that happened to them. How does your attention span change when they switch from listing off an itinerary to an actual story about getting in trouble? People love stories. Stories provide context and generate empathy. Stories reach the emotional parts of our mind rather than just the logical parts that data often does. Scientifically minded people often think that throwing facts, numbers, or statistics at people will win them allies and get people over to their side. But especially in America, though really in a lot of places as well, this false assumption has led to a decline in people's enthusiasm for science as both a hobby and as a thing that needs to get funded. We're just beginning to see a new movement of science communicators getting the public excited about science, the likes of which we haven't seen since the space race. Understanding how to communicate a story takes practice. People sometimes have an easier time telling stories with words than with images. The 2 often do go along together in the form of an image caption and labels or a video narration. But beware, you still have to be careful with your choice of words when you're describing a visualization. Dr. Karahalios and her colleagues at the University of Illinois have done some incredibly fascinating research on the effect that titles have on the perceived message of visualizations. It boils down to, and these are my words, not hers, that regardless of what a visualization shows, people are more likely to remember what they're told over what they see. One of the studies that she did was to show this visualization to a group of participants, which shows the number of Syrian refugees accepted by each of these listed countries. The obvious thing about this graph is that Germany, over here, has accepted overwhelmingly more refugees than any other country listed. Canada is over here in second place, and everything else seems pretty negligible. The US is way down here with 0.005% of the population. But the title of the graph that she showed to these people was "The US has accepted more Syrian refugees than the UK, Italy, Russia, and Finland combined." That's probably not a conclusion that you would have drawn yourself by looking at this data or looking at this visualization, but it is true if you add up the numbers in the left column. When asked sometime later, though, to recall the main message of this visualization, participants recalled that the US and Germany have accepted more refugees than most countries even combined, which is not what the message of the visualization was. Later on, when asked about potential biases in what they had seen, 83% of the participants were sure that there weren't any. Here's a selection of quotes from some of them. "It's fact. How can it be biased? It just shows the facts with no real commentary either way. Numbers do not lie. The graph is what it is. The information is not telling us what to do or what to think. It's just listing facts." So this is worrisome, right? People tend to believe things if they're backed up by data, citations, and visualizations without actually doing their own investigation of the materials. We, as visualization creators, have to be very careful not only about what we show in our visualizations, but also what we say about it and what context we put around it. Although visualizations can certainly come with titles and labels and figure captions or a video narration that tells the audience what to make of the visualization, the images should be able to tell a story on their own, even without text or narration. Think of any iconic photograph that you've seen. The moment you look at it, you immediately understand that something has led to the moments in the photograph. There's an implied history, decisions made that led to this point. Compare this dynamic photograph of the Washington Square Arch in Washington, D.C., to this photo of the same arch, also showing a group of people. This photo is arguably more aesthetically pleasing, but it doesn't tell a story like the previous photo does. Sometimes you won't be able to have complete control over the context in which your visualization will be seen. A lot of the work that my team does is freely open to the public, so we're often surprised to see it on the front page of Reddit, in other documentaries, and on really random corners of the internet. Images can get shared and reposted, paper figures get moved and resized, findings get sensationalized by social media, videos get re-edited, and so on and so forth. You'll want to make an effort to have your imagery tell its story without relying on the text of your paper or a description, because that might just end up getting stripped away. Just like the photo of the protesters at the Washington Square Arch, which tells a story without any text to describe what's happening. On its own, the imagery might not say everything that you want your audience to know, but it should be resilient against at least misinterpretation when seen secondhand. A problem with visualization in general is that it's subjective, on both the creating end as well as the receiving end. A data set can be visualized in a variety of different ways by the creator, and different people looking at the same visualization can interpret it in different ways. Furthermore, visualizations can be biased. The underlying data can be biased as well, but that's another subject for another day. And in the worst case scenario, a visualization can outright present the data in a way that tells the exact opposite story of what the data actually says. Now that doesn't really sound like it makes sense, does it? But here's an example. I'll give you a second to look at this visualization. Can you tell what's wrong with it? If you haven't noticed, the y-axis is upside down. 0 is up here, and these numbers, which are positive, increase in the downgoing direction. So this makes gun deaths seem to decrease. Whoops, skipped ahead, sorry. This makes the gun deaths seem to decrease instead of increase. Now, there's not really a way to know if this visualization was made maliciously to lie to people about gun violence, because that is a politicized issue, or if it was an honest mistake where someone just wanted to make a unique graph that looks cool using, a new graphical strategy. The creator claims that it's the latter, it was an honest mistake. But does it really matter what the intent was when the effect is the same, and this gets posted on the internet and seen by hundreds of thousands of people who then think that gun deaths are decreasing when that's just a blatant lie? Here's another problematic visualization. Sorry, I gave you a peek at it a little bit ago. Any ideas what's wrong with this one? It's a little bit trickier. The problem here is that 0 is all the way up here. And everything in this space looks like it's data, when in fact it's just filler content. One common guideline in information visualization is called the principle of proportional ink, which says that the colored area of an infographic should be proportional to the data values being communicated. This means a visualization should always keep the size of a colored region proportional to the value that it's representing. Here's an abstract example that breaks down some other potential issues in visualization storytelling. Here is a bar chart with ratings of 3 abstract objects called A, B, and C. In this graph, we can assume that C is rated more highly and is therefore much better than objects A or B. We might not notice that the y-axis doesn't start at 0 and that we're looking at a very narrow range of numbers here. If we rescale the y-axis to go from 0% to 100%, it turns out that A, B, and C are about equal. Sure, C is a little bit better, but certainly not as much better as this first chart implied. But perhaps this isn't the full story either. Maybe we were just looking at a subset of the full data set. This graph introduces D, which has a much higher value than A, B, or C. So all of these graphs show the same data in the same bar graph format, but they tell different stories. These graphs can't be correctly interpreted if their context in the axes isn't properly shown. If in order to tell an effective story, you do want to focus your visualization on a subset of your data set, consider following an overview and detail model in order to maintain context, if there's any concern that your visualization will be misinterpreted without that context. There are a number of different ways that something like this can be done, often seen in maps, but this can be applied to any sort of visualization. The same data can be visualized in a variety of different ways to tell a variety of different stories, and you can easily spin a data set to tell the story that you want it to tell, whether that's on purpose or by accident. Some visualization choices are better than others. If there's one thing that I want you to take away from this lesson, it's that there's no such thing as a purely objective visualization that doesn't tell any story. Whether you're aware of it or not, any visualization involves making design decisions that alter its story. Here's an example in a 3D scientific visualization. These 4 images show the exact same colliding galaxy data at the exact same moments, but they have significant differences. In A, we're looking at just the stars in the data set, and we're emphasizing regions of rapid star growth. In B, we're also just looking at the stars, but we've added motion blur which shows the motion of the stars and suggests movement to the viewer, so that even looking at just a still image, you get a sense for how the data is moving over time. In C, we're looking at the stars, but also adding gas. And the gas is being colored by which of the two galaxies it started up in. In D, once again, we're visualizing stars and gas, and the only difference is in the coloring. Now we're coloring the gas by the destination galaxy that it will end up in. Each of these representations uses the same data to tell a different narrative. You can't show everything in a visualization at once, most of the time, depending on how complex your data is. So you have to choose which variables to show, just the stars, just the gas, a combination of the two, and how to represent them in terms of color and other visual attributes. The last two galaxy images used color to tell a part of its story. Most people don't realize how much of an important impact color has on us and how we understand the world around us. But professional designers are hyper-aware of how color affects our moods and our actions. Each color tends to be associated with different feelings, some positive and some negative. For example, green might be associated with plant life and convey freshness and peace, although it can also be associated with sickness and convey uneasiness, which is kind of the opposite of freshness and peace. Red is often considered a color of passion. Here it's shown as passionate anger because red is the color of fiery hell, or passionate romance because blood is red and it makes our cheeks blush. Colors don't have objective meaning, but context can sway the feelings that an audience gets from them. Not only are individual colors meaningful, but so are different combinations of colors. Understanding how to choose a palette of multiple colors is an important design skill. A common tool for understanding relationships between colors is the classic color wheel. One of the most common ways to select two colors that work well together is by choosing complementary colors, which create a visual balance. They're on opposite ends of the color wheel. They're considered cheerful and bold, but can also be considered too obvious at times. Blue and orange is a favorite combination of complementary colors of designers in Hollywood because it heightens the drama of the orange tones in the actor's skin. It is very common. Once you've noticed this, you're going to see it everywhere, so I'm sorry if I ruined movies for you. Another example of a color combination scheme uses analogous colors. These are colors that sit next to each other on the color wheel, such as red, orange, and yellow. Together, these make a soft, non-offensive design that feels harmonious, but can get visually boring. Analogous colors also divide the color wheel in half into relative psychological temperatures, where red, orange, and yellow are considered to be warm colors, and the opposite colors, green, blue, and purple, are considered cool colors. Often, designers seek contrast in color temperature to create visual interest. There are many tools online that can help you choose color palettes for different kinds of purposes, and I recommend playing with some of them to understand what color combinations appeal to you. How are they related, and what do they remind you of? ColorBrewer is one of my favorites. Though it shows the colors on a map, you can ignore that part. It still offers up multiple options for color schemes. It makes you think about whether the data you're coloring is sequential, diverging, or qualitative. Sequential data goes from low to high values, where there's not necessarily a single value in the middle that's more interesting than the others. Diverging data has a defined value at some point in the middle that separates the data in some way. Say 0 degrees Celsius separates below freezing temperatures from above freezing temperatures. It's a good idea to use different categories of colors for each of those meanings to separate those two and visually tell that story. ColorBrewer likes to use the color white to mark the middle point. You don't necessarily have to do that, but you do want some kind of hard transition between the two other ends. Qualitative data is categorical, say to separate planets that belong to the Kepler 186 system from those in the 185 system and other systems. I've mostly been focusing on one aspect of color so far, which is called hue. And you can think about hue as where on the rainbow the color falls. But there are two other pieces to every color: saturation and value, which have an effect on psychology as well. You might say saturation is how vibrant the color is. You can see as you go out to the circle, these colors are very vibrant and these are more subdued. Here's a picture of a baboon that I'm going to use as an example to show you some of these different changes in saturation and value. So watch what happens as I turn the saturation way up. Saturated colors can be exciting and attention-getting, but sometimes artificial and can be thought of as childish. Here I'm exaggerating the saturation, probably a lot more than you'd ever want to do in a real-life setting, but I'm just trying to illustrate this point. A desaturated color is closer to gray. Desaturated colors can feel more natural and calm, but if you overdo it, like I did here, they might feel lifeless or decayed. So now our baboon is back to neutral. Next we'll talk about a color's brightness or value, which defines how light or how dark it is. Bright colors are light and optimistic, but high values can feel harsh. As you remove brightness from a color, it gets darker. Dark colors can feel mysterious, but sometimes they make details hard to distinguish. That can be a good thing if you're trying to hide clutter in part of your visualization. Contrast between color ranges is measured by the relative brightness of colors and makes brighter colors in a design stand out clearly. Contrast can be used to draw your eyes to specific data points and to de-emphasize others. So this is an excellent way to convey a story. You can highlight a specific piece of your data set by using contrast while hiding the parts, not hiding, but de-emphasizing the parts that are less relevant to your story. Different colors on the color wheel actually naturally have different brightnesses. Yellow is just naturally a bright color. You can see that it's much brighter than, say, blue. When you're choosing colors for your visualization, it's often good practice to actually preview your visualization in grayscale to see if it still tells the same story. People who are colorblind normally don't see in grayscale. Some do, actually, but people who are colorblind might not see a couple different colors. But looking at your visualization in grayscale will help you not have to rely on just hue, but will make you think about saturation and brightness, and will help colorblind people make more sense of your images if you design a color palette that works both in full color as well as grayscale. Monochromatic color schemes combine colors that have the same hue but different brightnesses, like in this combination of colors going from pink to deep red. So here, both hue and saturation and value, actually, are all being utilized in a way that the data makes sense no matter which of the three elements you look at individually. When you look at the world around you, pay attention to what colors are being chosen and analyze why they're effective. Why do all these fast food chains use red and yellow for their logos? They've done a lot of research and spent a lot of money figuring out that these colors are especially effective for whatever goals it is that they might have. Why is it that comedy movies are marketed with bright colors and thrillers are marketed with dark colors? Why is it that summer clothing is saturated and winter clothing is pale? You might start to notice another thing that designers understand very well. Different cultures assign different meanings to colors. Think about country flags, for instance. The flag of the United States uses the color red to symbolize bravery, but the flag of China uses the color red to symbolize revolution. In most cultures with cars, the colors red and green imply stop and go, but in places without roads, that meaning doesn't exist. Meanwhile, the combination of red and green in the Western world is highly associated with the Christian holiday of Christmas. But in the Eastern world, that same color combination is associated with Islam. Also note that red and green is one of the more common types of color blindness, so there's a lot of different reasons to be cautious when you're using these colors. Color is also political. Many people today are learning to be more cautious about the way they use the color words black and white. In majority white society, black has been treated as a scary color because historically it was associated with a fear of the unfamiliar, specifically people with dark skin. This is why we are discouraged from using terms like blacklisting and whitelisting. But the same is true for design. It might be your instinct to imply that something is a negative value by making it black, but this reinforces an antisocial stereotype and might alienate members of your audience. Of course, not all color associations are quite so high stakes, but understanding the cultural implications of your color choices can help you to avoid confusing and possibly even offending your audience. Temperature is an example of cultural confusion that you might already be familiar with in the context of astronomy. Most people see temperature indicators in their home and in their lives every single day, on sink faucets or stovetops, and these label low temperatures with the color blue and high temperatures with the color red. Ice is kind of bluish and fire is kind of reddish, so this makes intuitive sense. But this common use of color temperature becomes problematic when we start mapping color to extremely hot astronomical objects. Stars are one kind of black body object, which emits color according to this color chart, where the red and blue are reversed from what you see on your faucet at home. As black body objects get hotter, they become less red and more blue. This kind of counterintuitive representation occurs frequently, not just in black body objects and temperature, but different sorts of colors as well. And it's important to be aware of your audience's pre-existing biases and beliefs, and to keep your audience in mind when making color choices that might be common in your field, but might be different from what your audience expects. If conventions exist in your field for certain colors having certain meanings, do use them where possible because they can act as a visual shorthand for quickly getting concepts across. But be cognizant of possibilities for misinterpretation. In the US, the Republican Party is commonly referred to as red, and the Democratic Party is blue. Here's a map showing the results of the 2016 election, colored with these colors. Audiences would certainly get confused if you were to swap the meaning of these colors, even if you label them correctly. You might think audiences can look at the label and it could still make sense, but it's confusing because there exists this convention. It probably makes sense to color something like redshift red and not, say, green. But that's not to say that you should always do something just because it's how it's always been done. But if you're going to break a convention, you should have a good reason for it and put thought into what the implications are. A good convention that I encourage you to break is the common use of every color in the rainbow for quantitative data. Using many colors in a visualization is popular because it lets you highlight more features, but it's perceptually confusing. The color wheel is a wheel. The circles go around and round. There isn't an exact start point and end point. So looking at this image, can you tell whether blue represents a higher or lower value than red? You can't tell. Rainbow color palettes are inherently difficult to read. Using the rainbow makes sense for categorical data, where the values don't have an ordering, but never for quantitative data. If it's used correctly, color is a great shorthand method of quickly getting across a concept in a visualization. But color is just one of many visual attributes at your disposal. Depending on the type of data you're working with, different types of visual attributes are more effective and easier for humans to map to data values. This chart shows them ranked in order from most effective to least effective from a standpoint of human perception. Quantitative data values are numerical, as we've established. Sequential data refers to non-numerical but still ordered data values. For example, the sizes small, medium, and large. You know that small is less than medium is less than large, but you don't know exactly by how much or how they compare to one another. Categorical data refers to values where you can directly establish an order, say galaxies. Is the Milky Way galaxy more or less than the Andromeda galaxy? It's neither, it's just different. Notice that color, while it's very powerful at communicating story and emotion, is not that great at communicating exact data values. So it's a good idea to use it simultaneously with other visual attributes. You don't often just use one of these at a time, but a combination of them in a visualization. No matter the type of data, position is always the strongest visual cue. If you're making a scatter plot with X and Y axes, the position of a data point is the most obvious and easiest piece of information to understand. Notice that in a pie chart like this one, in addition to color, the visual attributes being utilized are angle and area. In this particular visualization, it's a bit hard to tell apart the largest slice of the pie chart. There are three likely contenders. This wedge here, this one here, and this one over here. Here's where the visual attributes of our pie chart fall on the list. Color, hue, area, and angle. They're not terrible, they're not all the way at the bottom, but we could do better. They're not all the way at the top either. This visualization shows the same data visualized as a stacked bar chart instead of a pie chart. This still demonstrates parts of a whole, but reduces the visualization from 2 dimensions to 1 dimension. Now we're only looking at the height of the bar instead of the width and height as well as angle. You can see that length is a stronger cue than area. This little animation shows many of the visual attributes from the previous slides mapped onto one data set. We can change objects in the scene to have data-driven positions, or sizes, or colors, or shapes. In animated video, we can drive motion with data as well. Here's a handy little cheat sheet that you can use to reference which visualization type to use for different kinds of data. You can take a screenshot of this for future reference. This doesn't list all of them, but just, line charts, bar charts, scatter plots, which are kind of the most common. Mapping a concept like color or length to a data value is a type of abstraction. And abstraction is a very powerful tool in visualization. This visualization is of a tornado, and it is filled with abstractions. Arrows on the ground are showing wind speed. Orange, blue stream tubes trace the wind direction. Balls near the center of the storm show areas of high pressure. And there's a faint gray shell around the storm, which is an outline of the storm cloud. These abstractions show us scientific information much more clearly than recorded video of a tornado or a realistic representation of a tornado. A real-world tornado is filled with dirt and fog, so it can be hard to see the inside of it. And we certainly can't tell by looking at it where changes in wind speed, temperature, and pressure occur. So using abstraction in this case actually simplifies and helps the audience better understand what's going on here. In both information visualization and scientific visualizations, arrows are a powerful abstraction that can be used not only to show flow in a data set, but can also be used simply to point out and emphasize an interesting feature in the data. I encourage you to use visual labels and visual cues to draw an audience's attention to the focal point of your narrative, especially in a complex visualization. Point things out by drawing circles around them, by drawing arrows to them and lines, and sorts of visual cues that are more easily understood by international audiences as well. There's lots of reasons to use these over just explaining things in text. As you figure out the focal point of your narrative, be aware that you may face a dichotomy between the data's science narrative and the outreach narrative. The science narrative is the story of the research that created the data. What question were you asking as a researcher, and how does this data get us closer to answering it? The outreach narrative is the story that you're trying to tell to someone to promote some broader understanding of science. If the story that you're telling is in your research publication, these two narratives might be the same, or at least similar. But if you're giving a presentation on your field of study to a more general audience, the outreach narrative might focus on a different aspect than the science narrative. In some cases where you're collaborating with other researchers, the outreach story might not even be focusing on your field of research. Here's an example of that. In this visualization, the science narrative was about how solar plasma affects the Earth's magnetic field. It was focused on how the turbulence of the magnetic field causes it to break down. The dataset didn't have the Earth in it because it wasn't concerned about the effects on the Earth, just around it, and was just showing the solar plasma. But the outreach narrative was about how a burst of solar plasma could be hazardous to life on Earth, not to the magnetic field of Earth, but to people on Earth. You can see in the visualization that all movement is centered around the Earth, which we added to the scene, and we kept the turbulent swirls of the magnetic field as a dynamic environment, even though they were the focus of the research. In order to tell a story well, it's helpful to understand the common traits in all stories. While finding new ways to use old storytelling techniques makes the stories feel original, we continue to use the same techniques that we've been using for millennia because they appeal to our human psychology. In short, we can transform a list of events into a story by introducing two things: characters and conflict. For instance, Little Red Riding Hood, without the scary forest and the big bad wolf, just becomes a story about a girl bringing her grandma bread. There's no lesson to be learned about traveling safely. Without his ghosts and the fear of failure, Ebenezer Scrooge would never learn to be a better man. And without apartheid and political adversaries, Nelson Mandela wouldn't have found his hero's voice. Freytags Pyramid sums this up nicely. This is a simple diagram that helps story writers remember the key elements to an effective story. First, you have the setup, or exposition, where you introduce the characters and the setting. In the four-wheeler story that I told at the beginning of this lecture, this is where I introduce my group of friends and how the vehicle got stuck in the river in the first place. Second, you have the rising action, in which a conflict is introduced and made more severe. In my story, the conflict is that we try to pull the four-wheeler out of the water, but the situation keeps getting worse, with the popped truck tire and the tractor almost falling into the water. Third, you have the climax, and the falling action, which is often brief, ending with the resolution. The climax is where the main character overcomes the conflict, and the falling action allows the conflict to be completely resolved. In my story, this is where we pull the tractor out of the water, right off into the sunset, and live happily ever after. People who are new to story writing often neglect the resolution, or replace it with a cliffhanger like "to be continued." Audiences find stories without an ending very unsatisfying, so it's highly recommended to include a thorough conclusion. So a good story has a beginning, a middle, and an ending. There's a number of different ways you can describe such a sequence visually. An annotated chart is a graph with labels that draws a user's attention and guides the story. A partitioned poster sets up a flow based on the poster layout. This can alternate between images, text, visualizations, and other content. A slideshow is a series of scenes, which can also have images, text, video, and anything else, shown to an audience one at a time in a particular order. A flowchart is a layout of scenes with boxes and arrows to guide the viewer because all of the scenes are shown all at once. A comic strip is similar to a flowchart, laying out all the scenes but without the guiding arrows. Note that comic strips are read in different orders in different cultures. A magazine lets viewers bounce back and forth between looking at text and figures. This is what a publication would fall under. And a video is a one-directional series of images that viewers can either play or pause. In science stories, identifying good characters and conflicts can be difficult. In text and in video, you can get away with having the characters be the scientists that are doing the research, and the conflict is them trying to find an answer to a critical scientific problem. For example, when the first image of a black hole was released in 2019, much of the public interest was around one young underdog scientist who, against all odds, achieved the impossible. But when we talk about a visualization telling a story of its own, it's often not practical to talk about human characters. Instead, we think of the science objects, like galaxies or supernovae, as the characters. This particular visualization had an accidental smiley face. It's not what I mean by a science character, but is cute nevertheless. Here's an actual example. This visualization is about the formation of our solar system, but it starts out with a wider picture, showing the contextual molecular cloud before introducing our main character, the protoplanetary disk. It's introduced as a seemingly small and insignificant piece of the universe that, in the next few minutes of the documentary, goes on to produce amazing things. It creates our planets, it creates the Earth, and eventually life. Scientific characters are abstract and harder for audiences to naturally connect with than other humans. This is why it can help to focus on a human-centered narrative and find the elements of the science that are relevant to daily life on Earth. Many audiences do find astronomy interesting, but it can sometimes be difficult for them to know why they should care, why it's worth investing time, money, and effort into answering astronomical research questions beyond just for the fun of it. Tying the story back to humans is a good way to make the science relevant. Science communication is a hot topic right now, but explaining new science concepts and discoveries to people is a hard problem. You might think that you're being perfectly clear, but your message might not be coming across the way that you think it is. It's always a good idea to show your visualizations to a few different people outside of your immediate research group to see if they understand the concepts. My team identified a few years ago that our audiences have a hard time telling apart the difference between our photorealistic data visualizations, made-up artistic illustrations, and photographs taken by telescopes. We've started showing previews of our documentary films to test audiences and handing out surveys with questions like this to see what our audiences do and don't understand, while there's still time for us to make changes to the documentary script. A large-scale formal approach like this might not be practical for you, but you can still get value out of informally asking 2 or 3 friends what they think of your visualization. Given enough experience and practice, you'll start to build an intuition for storytelling with visualization. In human-centered design, it's important to always keep your audience at the core of every decision. Don't mold your story around your facts, mold your story around your audience. There are many, many ways to visualize a data set, showing different combinations of variables, showing a subset of the data, putting it in a different context, using a different type of chart, picking different colors and visual attributes, and so on and so forth. Experiment with different options, get feedback, and iterate whenever you can. You'll be telling captivating stories in no time. Thanks.